Welcome to the Communication Engineering Lab. And in this video, we are going to conduct one experiment. And the objective of this experiment is to construct a square wave. So we have to write a MATLAB program to construct a square wave with the help of fundamental frequency and its harmonic component. So here you can see we have this symmetrical square wave, which is symmetrical around time axis, and it is also symmetrical around this amplitude axis. So the square wave that we have taken is having its fundamental period equals to T naught, which is related to its fundamental frequency F naught by this particular expression T naught equals to 1 upon F naught. So normally, if we have any periodic square wave, then this wave can be represented by its equivalent trigonometric Fourier series. And that Fourier series expression is given by this particular expression. Here you can see this is the equivalent trigonometric Fourier series. Okay. So here I'm not going to derive this particular expression, how this expression comes, but this will be left for exercise to the students who are watching this video. Okay. So please go and try to derive this particular expression, right? So here is the expression, okay, the equivalent trigonometric Fourier series representation of this particular square wave. So this CT is given by 4 upon pi, and there will be a summation over n equals to all odd numbers 1, 3, 5, 7 up to infinity. And here this amplitude is given as -1 to the power n minus 1 divided by 2 divided by n cos n omega naught t. So here we can see this summation will actually go over all odd values of n. Okay. So, and this summation will go up to infinity. So if we generate such cosine signals, okay, if we generate such cosine signals, then if we add all those infinite harmonics, then we will be able to construct this particular square wave. So that we have to look at how this can be done. Okay. So let's try to expand this expression. Okay, then we'll go to the MATLAB and then we will write the code for it. So here you can see, because this summation will go up to infinity, but normally while writing the programs, we cannot take infinite summation. So we have to go for the finite summation, right? So here you can see, if we restrict ourselves to a certain finite values of n, then we can expand this particular relation, okay, this particular equation, right? So here you can see this amplitude is 4 upon pi. So let's try to assume that this 4 upon pi is denoted by a. Let's assume that this 4 upon pi is denoted by a. And then if you take this values of n, okay, if you let us suppose n is equals to 1, in that case, this value here you can calculate. This n is equals to 1. So 1 minus 1 divided by 2. So it will become 0 upon 2. So -1 to the power 0 will give you value equals to 1. Okay. So it is 1 divided by 1, and here it is cos n omega naught t. So this omega naught can be written as 2 pi f naught, where f naught is the fundamental frequency, and n is equals to 1. So in this case, this will become cos 2 pi f naught t, right? So if we expand this equation for n equals to 1, 3, 5, 7, and so on, then this expression you can easily find that for n equals to 1, the first term is going to be a into cos 2 pi f naught t. Similarly, if you substitute n equals to 3, in that case, you will find that this is 3 minus 1 divided by 2. So you will be getting 2 upon 2, means this power is an odd number. So when it is an odd number, in that case, this -1 to the power an odd number will become negative sign. Okay. So here I'm just putting this negative sign, and this amplitude will become, this is your A, and this is n value is here equals to 3. So this amplitude will become a by 3. Okay, so here you can write a by 3. Similarly, this term will become cos 2 pi 3 f naught t. Similarly, if you substitute n equals to 5, you will find that this sign is going to be positive, and this amplitude will become a upon 5. And here you can find this is cos 2 pi 5 f naught t. Similarly, you will get the rest of the term, right? So you will find that this sign will be, alternatively, it will become like positive, negative, and so on, right? So here it is negative, the next sign will be positive. So this will go up to infinity. So here, corresponding to n equals to 1, this will be giving you the fundamental frequency component. So cos 2 pi f naught t is giving you the fundamental frequency component, and all rest of the terms like 3f naught, 5f naught, 7f naught, 9f naught, and so on, it will be giving you the odd harmonic components, right? So now we have to write a MATLAB program for a particular value of n, and then we have to try to see whether if we generate this particular signals, and if we add all the signals by considering this sign and amplitude, then you will find that this summation is going to approximately equal to this particular square wave. So that we have to see. Okay. So for this, I will be going to the MATLAB. Okay. And there we will try to see this code. Okay. So I will be using the same expression, whatever I have explained here onto the MATLAB. So here you can see I have already written this code. So here you can just try to see this code. Okay. So here you can see the first line is clear in CLC command. So this clear will clear the command window. It will clear the variable in the workspace, and this CLC will clear the command window. Okay, command window screen. So here I have taken this fundamental frequency f naught equals to 100 hertz. And here I'm just trying to make this time array. Okay. So this time array I have taken to be equals to minus 10 divided by f naught. So here you can see 1 upon f naught will give you the fundamental means it's time period of the square wave. So if you multiply it with this multiplicative factor 10, then 10 multiplied with time period will give you total 10 number of such cycles. Okay. So here I'm just taking in the negative direction, I'm taking 10 number of cycles, and also I'm in the positive direction, I'm taking the another 10 number of cycles. So altogether from this time duration to this particular time duration, we are going to get in totality, we are going to get a total 20 cycles, right? So that we can control. So here you can see this is our time array in which we have to give the starting value and we have to give the ending value of this particular time array. And here we have the step size of this particular time array. Okay. So I have taken this step size equals to T naught divided by 1000, right? So that 1000 means this value will be very small or sufficiently small so that we are going to get the very good plot. Okay. Its visibility will be very clear. Okay. So that's why we are just taking T naught divided by 1000. You can even make T naught divided by 100. Okay, even in that time, we will be able to see the plot properly, right? But you cannot make it too small, right? Too large, right? So just appropriately, we have to choose this factor, right? So here I have just defined this a equals to 4 upon pi. And then now I have just defined the expression that I have wrote there. So this y1 is now consist of the first fundamental frequency cos 2 pi f naught t. Then I have taken the first odd harmonics. So this is my first harmonic term, 3f naught term. Then I have taken the second harmonic, 5f naught term. Then third harmonic term is 7f naught term, f naught. Okay. So up to this, here you can see I have written this code. Okay. So in y1, if you see this particular code, in y1, I have considered only first harmonic. We have considered the first fundamental frequency. I have just considered the fundamental frequency and first three harmonic terms I have considered. So now we can plot this y1, okay, this particular signal y1, we can plot with respect to time array t, right? So here I have taken this subplot function, and then you can use this plot function here in which we have to plot this two variables t and y1, okay? So here you can choose this line width parameter to just make the lines to look more broader. Okay, the thickness of the line will be more so that its visibility will be more clearer. Okay, so here you can take this line width equals to 1, and I have just given the title in which I have written that I have taken the fundamental frequency and plus first three odd harmonics. So this plot I will show you while executing the code. But here you can see in the next line, what I done is here you can see I have already generated the y1, which consists of its fundamental frequency and first three odd harmonic terms. Okay, so here I have added more harmonic terms. You can see that. Okay, here because I have already y1 is generated, so within the same y1 I have extended this equation. Okay, so here you can see I had this last sign is negative sign, so after that we are going to get the positive sign. So I am putting here positive sign here, and then I have written the next harmonic term, which is 9f naught term. Similarly, the next harmonic term will be your 11f naught, then again 13f naught, and then again it will be 15f naught, right? So in this way, here you can see I have added 1 2 3 4 and 5. So in totality, here you can see in this case, I have added four additional harmonic terms, and here I have already added three uh, harmonic terms in y1. Okay, so in total here you can see in this y2, we are going to get fundamental frequency f naught, and we are adding the first seven odd harmonic terms, right? So similarly, I have added more harmonic terms in signal y3. Okay, so because I have already generated up to y2, so I am just adding this y2 terms, and then I have added more harmonic terms, right? So here you can see 17f naught, okay, then 19f naught, 21f naught, 23f naught, and so on, right? So here you can see in the last plot, I have considered fundamental frequency f naught and the first 12 odd harmonic terms I have added. Okay, and then we can see what kind of results we can observe. Okay, so here you can see I have added up to 25 f naught, right? So now if we execute this code, okay, if you run this code, you will be able to observe this result. Okay, so we have this three plots. One is corresponding to f naught plus three odd harmonic terms. And then the second plot will consist of seven odd harmonic terms, and the last plot will be consist of 12 odd harmonic terms, right? So here you can see this is the plot. Okay, so here you can easily see this picture. Okay, so here is the first y1 plot. Okay, so here you can see this is the y1 plot, and I had taken this wave to be symmetrical around time axis. So this is your time axis t equals to 0. And from this 0 to 0.1, we are going to get this 10 cycles. Okay, you can easily count this cycle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, similarly, in the negative side, we are also having the 10 cycles. So this is the first y1 plot. Okay, and here you can see this is the y2 plot. So in the y1 plot, we are having fundamental frequency plus first three odd harmonic terms. Similarly, the second plot, we are having the fundamental frequency plus first seven odd harmonic terms. Similarly, here you can see in this third plot, this is the y3 plot. So here you can again see this is consist of first fundamental, this is your fundamental frequency and the first 12 odd harmonic terms. So here you can see in the differences in this plot is that when we are increasing the number of harmonic terms, okay? So when we just took only three odd harmonic terms, then this waveform is actually having a lots of fluctuation in this section, okay? So though we are trying to generate the square wave, but here you can see it is not perfectly looking like a square wave, okay? There is a fluctuation, or you can say there is a ripple in this particular section, right? But this ripple or this fluctuation in the amplitude is going to reduce if we increase the number of odd harmonic terms. So here you can see even from 3 to 7, this fluctuation is now going to reduce. Okay. Similarly, when we have taken 12 odd harmonic terms, then this is further reducing, right? So basically, here we can easily see that if we increase the number of harmonic terms, okay, to generate the square wave, the waveform that is going to appear will be much more closely, or it will be approximated as equals to a square wave. So obviously, when we are going to have the infinite number of odd harmonic terms, the waveform that we are going to generate, this must be equal to your square wave. So I hope you must be able to understand this particular program. So try to write the same code and try to execute it, and try to observe this result. You can also do one more thing is that in this program, I have just taken 12 odd harmonic terms. Okay, so you can increase the number of harmonic terms. Okay, you can go up to 21, 25, or 30, and then you can try to observe that the waveform will be more closely equals to your square wave. Okay, so that you can observe. So now I will stop here. So try to execute this code. And if you have any doubt, let me know with your comments. So thank you for watching this video. And if you have any query, let me know with your comments. Thank you.